So in this talk, we'll be discussing about property P in connection with operator algebras. Let me first go on and actually record this fundamental concept. So group gamma has countdown property T. If any possible unitary representation of the group gamma, if it has almost invariant vectors, we have non-zero invariant vectors. And we all know these standard examples. Lattices in high rank separable groups as S and Z. So property T has quite a strong applications, and it's useful in fields like operator algebras, ergodic theory. Before mentioning our main result, let me actually recall this result of Ossian-Stills-Sand, which says that every possible countable group gamma can stay inside a property T group. And how do you prove this statement? Well, let's look at this notion of SQ universality. So group H is said to be SQ universal if any possible group gamma will embed into a quotient of this group H. And this notion has been studied for a while. So free groups are SQ universal. More recently, non-elementary hyperbolic groups are SQ universal, and this will be useful for our result mentioned above. And actually more general groups, so-called accidental hyperbolic groups, which include a much larger class of groups in hyperbolic groups, including, for instance, mapping class groups and so on. And now the small remark having all this is saying that if one is looking to a co-compact lattice in SPN1, this lattice has to have property T and is hyperbolic. And being hyperbolic means that it's actually universal, so therefore an arbitrary group will embed into a quotient of this lattice. And we know that property T passes to quotient, so therefore one obtains the above state. Well, okay. So on my last line was written that the main goal of this talk is to give a Neumann algebraic analog of the notion of Ossian-Stills-Sand. So namely, that any tracial phenomenon algebra will be inside a property T phenomenon algebra. But I think I have two slides like that with the last line covered. Let's see how it works. Before going further, let me mention recalling that Kohn discovered that property T is useful in operator algebras by showing that if you have an ICC property T group, you cannot necessarily compute the out and the fundamental group of L of gamma, but at least you can see that they are countable. A few years later, Kohn together with Jones defined the notion of property T for Neumann algebras, which is saying that any M by module with almost central vectors will have a non-zero central vector. I'm not sure if we can review that.
Can I give it a try?
Well, it's not essential, but
this morning there was a mouse.
There's still a mouse. It's on the shelf below. Left. To the shelf there.
Yeah, thank you. Good point. Yes, nice. Okay, this notion of property T for fundamental algebra is as we want to be compatible with the notion of groups. And Kohn and Jones showed in particular that if you have an ICC countable group, the fundamental algebra has property T even if the group itself has constants property T. And now this notion of property T is a key concept. For instance, in orbital equivalence and in fundamental algebras, we gave rise to answering long-standing questions as computing, showing that the fundamental groups of certain fundamental algebras are trivial. So using Popper's deformation rigidity theory, in the last 2 decades, we obtained computation of outer group of fundamental algebra and the fundamental group. Now let me go ahead and specifically mention our result. So we have shown together with, oh yeah, I forgot to mention, so this is joint work, as was on the screen, Ionut and Adrian. So we showed in our main result that any separable tracial from Neumann algebra will embed into a two-1 factor with property T. In a few slides, I will give some ideas about this proof. So, as I mentioned already, this is an analog of the group theoretical result of which one's in the design. Our result also answers the questions of Scott, Isaac, and Sri. And at the end of the talk, I will mention a few results that are connected to their work. And this is a quick and obvious corollary that the tracial phenomena algebra is separable if and only if it embeds into a property T one factor. This is not necessarily surprising once we have this result. And a small remark is that if we recall Kant's embedding problem, which is stating that is any separable one factor embeddable into R omega, with R the hyperfinite one factor, and we know the answer is no by this recent paper. We of course obtain this corollary that you must have a property T to one factor that is not embeddable. Okay. Now, before saying some things about the proof, let me actually put everything. Let me formalize everything using this definition. So you can look to a class of two-1 factors, which is called embedding universal, if any possible separable two-1 factor will embed in one of these members. And in the literature, there already exist some classes of embedding universal. For instance, by the work of Jesse, the class of two-1 factors that are either prime or full. This class of is already embedding universal. Also by the work of Adrian, if you look to two-1 factors that do not have a countable algebra, again, this is embedding universal. And our result now is saying that the class of property T two-1 factors is embedding universal. But in contrast with the previous two results of Jesse of Adrian, so they are taking a phenomenon algebra M and embedded into something like this, the free product. It's a canonical clear embedding, and that's prime, full, and does not have a countable. What we do for our result, we have to use a more, I would say, non-canonical construction, and it relies on the so-called notion of Wreath-like product groups, which was introduced a year ago by Chifan, Ioana, Tosin, and Su. So I will say a few words on the next slide about these groups. Let me also make this small remark that if you have an embedding universal family, it has to be uncountable. So it has to be a huge one. This follows, for instance, from the result of Ozawa. So Ozawa, what he did, he constructed an uncountable family of group von Neumann algebras, and he showed that if you fix a separable two-1 factor, and if you look to how many of them can embed into this N, that has to be a countable set. And therefore, this already shows that since I is uncountable, it shows that F has to be uncountable. Okay. Now let me recall this notion of what does it mean to be a Wreath-like product group. So they imitate the notion of Wreath product groups, but it has an important property. So first, let me say that a group G is said to be a Wreath-like product group of A and B if the group G is set inside this short exact sequence. So the infinite direct sum of AB indexed by B, it's inside G, and G maps into the group. It goes onto the group B, and it satisfies this formula. So exactly as we have for Wreath product groups. So GAB, G minus 1 is exactly shifting. You look to a different A, and now the index is epsilon GB. And epsilon is exactly the quotient from G to B. We denote by this class of Wreath-like product groups. So all the groups that arise as written in the short exact sequence, we denote it by WRAB. And what's important is that, so the observation is that standard Wreath product groups belong to this class, but what's non-trivial and what's essential is that this class contains, in contrast to Wreath product groups, this class actually contains property T groups. And the authors actually showed a much more general result. For instance, they show that for any possible capital A finitely generated group, you can find a property T group in this class with B hyperbolics. It's actually a quite involved result constructed with this class of groups. Now, why did they introduce these groups? Is this old conjecture? So this, this conjecture of Cohn's rigidity conjecture, which says that any possible property ITC group is W star superrigid. So its phenomenon algebra recovers the group itself. So meaning if L of gamma is isomorphic and L of lambda arbitrary, the two groups have to be the same. And because of Popper's deformation rigidity theory, it has been discovered some classes of W star superrigid groups. So the first one goes back to the work of Adrian, Sorin, and Chifan. About 12 years ago, they showed that certain generalized Wreath-like groups would be W star superrigid, and also different groups like amalgamated free products and AGN extensions have been obtained to have this property, but both of these classes do not have property T. So the way they are constructed was to admit certain lots of deformations. So the machinery from Popper's deformation rigidity theory would work directly. So the authors, Chifan, Ioana, and Sun, what they did, they showed that if you consider this class of Wreath-like product groups, if you take an arbitrary group from there which has property T, and the group A to be abelian, and the group B to be ICC hyperbolic, all these groups G will be W star superrigid. Okay, so our result relies actually in this construction. I will now explain how. So let me recall the statement that we already seen a few slides ago. So if M is a separable two-1 factor, arbitrary one, you can find a larger property T2-1 factor that contains M. And in addition, we can actually assume that this new fundamental algebra P will have trivial out and trivial fundamental group. Now, let me say a few words about the proof. So first of all, we can look to M inside M tensor, the hyperfinite one factor. Why do we do this? Well, M tensor R can be easily seen to be generated by 3 unitaries. So therefore, we can assume that M is generated by 3 unitaries by the work of, so it's an observation in the work of Goethe and Popper. And hence, we can actually, let's define a homomorphism of the free group with 3 elements that goes onto the unitaries of M. And what we want will be, we want this homomorphism to generate the fundamental algebra M.
But the unitaries need not be in M.
Sorry?
The unitaries that generate M will be outside potentially.
Let's replace it.
So Sam, so what I'm saying is that we consider this pi for M tensor R, for instance.
Right. So the M in this line is like the old M.
Yes, exactly. I'm saying, let's assume without loss of generality because of the first line, that M is generated by 3 unitaries.
Yes.
Yes. Okay. Now, what's the key part and the most important part is that what we can do, because F3 is a finitely generated group, the result of Chifan, Ioana, and Sun says that we can obtain a property T group in this class. And this group also will have non-trivial characters and the out of B to be trivial. And this will be useful exactly in completing the last part of the proof. And what's the idea now is that the representation pi that we have here for F3 can be extended actually to a representation of the whole group G. And of course, we will have to map pi tilde to a different fundamental algebra called P. Why this holds? So the observation here is that any Wreath-like product group G has to be written as a semi-direct product arising from a co-cycled action. So of course, this is not a direct action because it will be a Wreath product group, and that's a perturbation, alpha is a co-cycle. And the fundamental algebra P that arises here is actually also arising from a co-cycled action on tracial fundamental algebra. And because of this, now if we put everything together, so the group G has property T as was chosen, and because of that, because pi tilde goes generating this fundamental algebra P, P itself will have property P, so that's all about the proof. Let me also just say a few words about the last part that I included here in this proof. So, as I said, that OPA deformation rigidity theory was helpful and led to computing this kind of invariance for 2-1 factors. So Popper showed first that the free group factors of this group, the fundamental group of the free group factor of this group is trivial. And a few years later, together with Adrian and Jesse, they found 2-1 factors that have not only fundamental group trivial, but also out to be trivial. And how we can also contrast our result with all this is by the following. If we denote by T the class of 2-1 factors with property T, we have trivial fundamental group and trivial out. We can look to the Popper strength of cone rigidity conjecture, which includes already John's conjecture. And a particular case of this conjecture is saying that if G is an ICC property T group with trivial out and no characters, then L of G will have to have fundamental group trivial and out trivial, and therefore L of G will be a 2-1 factor in this class T. The first examples of property 2-1 factor with trivial fundamental group have been found actually recently by Chifan, Fude, and Khan. And also last year it was shown that this class T will be uncountable. And what we can show in particular that it's not just uncountable, it is embedded universal. So this was the point that I wanted to make. That this class T that satisfies that it appears here in this conjecture of Popper, it's quite big, it's embedded universal. Now let me also make a few more observations. So what we are able to show is also that if M is an arbitrary separable 2-1 factor, and if H is any hyperbolic group, or more general acylindrically hyperbolic group, then what we can do, we can find a representation of H, so we can find a representation of H that will generate a 2-1 factor that includes M. And this result can be seen again as an analog of the SQ universality property that stands for groups, and in particular it applies to acylindrically hyperbolic groups. Right? I mean, it's showing that any 2-1 factor can be embedded into a 2-1 factor arising from a representation of the hyperbolic group. The proof goes along the same lines as I sketched the previous proof. The only thing is here we have to use is that any acylindrically hyperbolic group will admit a quotient which belongs to the class of Wreath-like product groups starting with F3. And again, will be the same machinery. Now, the observation that I want to make here is that we in particular can look to H to be a co-compact lattice in the rank 1 simple Lie groups, SPN1, because H will be hyperbolic. And what it's showing, our result is saying that the 2-1 factors generated by this lattice H is quite big, it's embedded universal. And this is in sharp contrast with the work of Jesse, saying that if G is an ICC lattice in a higher rank, in this case, simple Lie group, like SLN3, L of G will be the only 2-1 factor generated by representation of G. And this result attracted a lot of interest in the last years. So the first proof was, so for SLNZ, the proof was given by Becca, and recently Remy and Cyril generalized this result with new proof and so on. Okay. I want to mention also, briefly mention that we have an analog of this statement from phonema algebras to equivalence relations. So there's a notion of property T for equivalence relations, saying that an ergodic equivalence relation R has property T if any one cocycle with almost invariant vectors will have invariant unit vectors. And there's a connection between this notion and the notion of property T for phonema algebras, saying that so an equivalence relation R will have property T, but you also have to assume in addition that the inclusion of L infinity of x inside the phonema algebra of R has relative property T, and this will be equivalent with the phonema algebra of R to have property. So here this is a connection. And now the result I was saying that we have obtained is that we given some sort of analog to equivalence relations but we have an obstruction. So again, let me start with a countable p.m.p. equivalence relation on x mu. But we also have this trivial equivalence relation, let's say on a non-atomic probability space y mu. So although we cannot show that R embeds into a property T equivalence relation, we can show that the product between R with this trivial equivalence relation, this product equivalence relation will embed into a property T1. Well, will embed into S with L of S as property T, but in particular, S will have property T. Why can we obtain only this? Well, the idea is we mimic the proof from Neumann algebras, and if you remember how the big P was constructed, was like a Wreath product for Neumann algebra. And because there is tensor products, that's why we have it here and here. Okay. I still have a few minutes. Let me discuss now. Yeah, and we have also in addition this extra property for S. Let me discuss some consequences to embeddings into ultraproducts of our result. So first, let me fix this notation. Omega will be a free ultrafilter on N, and R will be the hyperfinite one factor. And here's the famous problem of Poppa's factorial relative commutant problem, which says that if you can embed M, a separable to one factor in R omega, can you do this embedding? Can you find another embedding which will have a trivial, which will have this relative commutant to be a factor? And examples will be the experiments show that R satisfies this, SL3Z will satisfy, and also more recently the work of Scott with Isaac and Sri shows that you can actually look to one factors that are elementary equivalent to R. So besides this class, now I don't think it's known too much about this problem, but recently Isaac considered different phonema algebras instead of R and obtained a more general solution. So let me quickly mention that there is a class of phonema algebras that arise from model theory, and those elements in this class G will be called infinitely generic one factors. This class of G we want to be embedding universal. We will also want to have that any embedding from one factor Q1 into the other one will extend to an isomorphism about ultraproducts, and we want G to be maximum with these properties. So Isaac Goldring showed that if Q is any infinitely generic to one factor, then any property T to one factor can embed. So M can be so any to one factor M can embed in Q omega with factorial relative commutant. And what we're able to do, we recovered this result and prove a more general result saying that actually any full to one factor can be embedded into the infinitely generic to one factor with ultra power with factorial relative commutant. So this is one of our applications. And we have another application to the study of so-called super McDuff to one factors. Let me briefly recall what this means. So to one factor M is said to be super McDuff if its central sequence for Neumann algebra is a to one factor. That's super McDuff. And there are a few classes of examples, for instance, hyperfinite one factor, first, also n tensor R with n to be full one factor, and also infinite tensor product of full one factors. All of these are super McDuff. And here's an open problem, again by the same Scott, Isaac, and Sri. So in their work, they also were wondering if one can find examples of two-one factors which are existentially closed. So essentially closed, so it's a bit too much to define, I think, but it includes the class of infinitely generic two-one factors. It's quite large. Can you find some of those to be super McDuff, or actually are all of them super McDuff two-one factors? And what we were able to show is that any infinitely generic two-one factor, so the class that was seen a slide ago, any such two-one factor is actually super McDuff. Okay, and the last application is that we can look to different class of this family which I didn't define, existentially closed factors, not just to these infinite generic one factors. And what we are able, we can study some tensor product decompositions. So using our main result, that any phonemic algebra embeds into a property P phonemic algebra, we were able to construct by an inductive limit procedure an embedded universal family of one factors. All of them will be existentially closed, for which they cannot be written as tensor products of one factors, and one of them to be a full one factor. Okay, and that will be everything.